Hi, everyone. Welcome back. We're going to be looking at Introduction to Chemical Equations for this particular section, Module 4. And the big goals are to understand information conveyed by balanced chemical equations, including the terminology used, reactants, products, stoichiometry, stoichiometric coefficients, and to recognize that a balanced chemical equation is required by the law of the conservation of matter. So here, we're going to take a look at a balanced chemical equation or balanced chemical equations, and we're going to be talking about the law of the conservation of matter, which is sometimes said as the law of conservation of mass. And so mass is conserved in chemical reactions. You can't lose it, you can't gain it. The amount of mass you begin with is the amount of mass you end with. And that has certain ramifications in chemical reactions. So this is an example of a chemical reaction where you have 2 sodium react with chlorine to give you 2 NaCl. Now remember, there are 7 elements that come in pairs of atoms. They are hydrogen, nitrogen, oxygen, chlorine, bromine, iodine, and fluorine. And chlorine, of course, is one of those. Now, for those elements that don't come in pairs like sodium, you won't have a 2 following the symbol. And here, when we look at this chemical reaction, the first thing that we want to recognize is that we have this arrow here, and that arrow means it becomes or forms or something like that, produces. I like the word produces because that tells you that this on the right are products. The arrow points towards products, and the arrow points away from reactants. So reactants are what you begin with, and products are what you end up with. So here's the same chemical reaction, and the focus now is on these things called coefficients. Coefficients tell you how many you have of a particular substance. So here, this substance is a pure element, sodium. The coefficient is 2, which means 2 sodium atoms, but it could also mean 2 mole of sodium atoms. And here, the coefficient is 1. If we don't write a number in front of the substance, the coefficient by default is 1. So this is 1 chlorine molecule, or 1 mole of chlorine. And here, when we have a 2 in front of the NaCl, it means 2 of the substance that follows. So not just 2 sodiums, but 2 of this whole formula. So 2 NaCl, and since this is not a molecule, we have to say formula units because that is a formula, or 2 mole of NaCl. So these coefficients can be substance ratios, or they can be mole ratios. In both cases, they are amount ratios. And now, well, I should also say that these ratios are called stoichiometric ratios, or these are called stoichiometric coefficients. Now let's focus on the states of matter. So here, you like to put in parentheses the letter S if the state of the matter is a solid, the letter G if the state of the matter is a gas, and here, again, a repeat. If the state of the matter is a solid, you put an S. So let's look at the law of conservation of matter in action here. So here, I'm going to look at these coefficients as numbers of the substance. So in this case, 2 atoms. And in this case, it's 1 chlorine molecule, but it's 2 chlorine atoms. So I'm reducing this down to the atom look, okay? So what does the 2 NaCl mean? Well, 2 NaCl means NaCl plus NaCl, and you can clearly see there's 2 sodiums and there's 2 chlorines. So 2 atoms of chlorine and 2 atoms of sodium. So we can see that when we make the list that these are balanced, 2, 2, 2, and 2. And we want to compare the right element with the right element, okay? So the reactants must have the same elements as the products when we're balancing. So the reactants have the elements sodium and chlorine. The products have the elements sodium and chlorine. The numbers of each element on the reactant side must equal the numbers of the same element on the product side. 2 sodiums on the reactant side, 2 sodiums on the product side. 2 chlorines on the reactant side, 2 chlorines on the product side. And we don't really care whether these are ions or not. We just care about the atom itself. So let's look at stoichiometric coefficients or stoichiometric ratios. So when we write out this balanced reaction, 2 sodium plus 1 chlorine gives you 2 sodium chloride. The way we normally talk about this is in a mole ratio. So 2 mole of sodium react with 1 mole of chlorine to make 2 mole of sodium chloride. And this is the equality. So when I write 2 mole of sodium equals 1 mole of chlorine, I know that sodium and chlorine aren't the same, but this is like a recipe. For every 2 mole of sodium, I need 1 mole of chlorine for this recipe. And I will produce 2 mole of sodium chloride. So this is kind of a recipe or an equality. And remember, when we have equalities, we can get ratios out of this, which we can use as conversion factors. So for this equality here, I can write 2 mole of sodium over 1 mole of chlorine. Or I can write 1 mole of chlorine over 2 mole of sodium. Or I can write 2 mole of sodium to 2 mole of sodium chloride. I can skip the chlorine altogether. So we can get these stoichiometric ratios, which are conversion factors, which we'll find very useful later, okay? So here's a question that we're going to look at. The equation for oxidation of phosphorus in air is P4 solid plus 5O2 gas gives you, this should be arrow, P4O10 solid. Identify the reactants and products and the stoichiometric coefficients. To what do the designations S and G refer? So if we write this out, you want to leave a good space between your 5 and your O, otherwise it'll look like 50. So identify the reactants. Those are the reactants. They always are at the end of the arrow where you're pointing away from them. And the arrow always points to the products. In this case, there's only one product. What are the stoichiometric coefficients? Are 1 to 5 to 1. And a better way to write this would be 1 mole of P4 to 5 mole of O2 to 1 mole of P4O10. And by the way, how would we say this name? Well, it's only nonmetals, so it's molecular. So we want to use a molecular name, which means the binary molecular name. So tetraphosphorus decoxide or decaoxide. Now, what do these refer to? This refers to solid, gas, and of course, solid. Here's another problem. The equation for the reaction of phosphorus and chlorine is P4, solid, plus 6Cl2 gas, gives you 4PCl3L. If you use 800 molecules of P4 in this reaction, how many molecules of Cl2 are required to consume the P4 completely? So I'm going to write this out again. And let's just make sure that this is balanced. So how many phosphorus is on the reactant side? Well, clearly there's just 4. How many on the product side? Well, since we have 4 PCl3s, there's 1 phosphorus for one of these formulas, and when you have 4 formulas, you have 4 phosphorus. A quick and dirty way to figure out how many of the element is just to multiply the coefficient by the subscript. So here the coefficient is 1. 1 times 4, there's 4 phosphorus. Here the coefficient is 4. 4 times 1, 4 phosphorus. So 4 and 4, that matches. Chlorines, 6 times 2, 6 chlorines. 4 times 3, 12, did I say 6? 6 times 2, 12 chlorines. 4 times 3, 12 chlorines. So this matches. Now, this says molecules rather than moles, so I'm going to write this a little bit differently. I'm going to put 1 molecule. Remember, the abbreviation for molecule is there is none. 6 molecules and 4 molecules. Whoops. PCl3. Now, the reason I can use molecules for all of these is because all of these are made out of only nonmetals. So if I start off with 8,000 molecules of P4, and I want to figure out the molecules of Cl2, so this is like my question mark here. If I can find a ratio between these two, I'll be able to do that. So in the best of all worlds, I would be able to find out the ratio of molecules of P4 to molecules of Cl2. And can I find that anywhere? And it's right up here. 6 molecules of Cl2 to 1 molecule of P4. So you can see that in this answer we have 8 times 6, which is 48, plus these 3 zeros. Okay. And this problem is not written the best way possible because this has only one significant figure. I mean, you're not going to be able to count 8,000 molecules of P4. They're too small. It's ridiculous. So this answer should only have 1 zig fig. Now, on the other hand, if this had been simply 8 molecules of P4, that would be something that we could count, presumably, and this would be 48. Okay, these stoichiometric coefficients have infinity significant figures because when you have a balanced reaction, those coefficients, for all intents and purposes, are counted. And they are counted reliably so that we know what the number is. It's no guess. Let's take a look at another one of these. Oxidation of 1 gram of carbon monoxide produces 1.57 grams of carbon dioxide. How many grams of oxygen were required in this reaction? So oxidation of carbon monoxide means the reaction with oxygen, okay? So here's the formula for carbon monoxide. 1 carbon, 1 oxygen. It's a gas. And it's going to react with oxygen, O2. It's a gas. And it's going to make 1.57 grams of carbon dioxide. And it's also a gas. We don't need to concern ourselves with whether or not this is balanced because actually it is not. 1 carbon on the reactant side, 1 carbon on the product side, that's good. 1, 2, 3 oxygens on the reactant side, 2 oxygens on the product side. This is not balanced. So we can do this problem without balancing it because we haven't talked about that yet. This is 1.00 grams. and this is 1.57 grams, and this is what we want to figure out. Well, what does the law of the conservation of matter say? Well, it says that 1.00 grams plus this question mark has to equal 1.57 grams. So question mark is clearly 0.57 grams, and that's our answer. That's how many grams of oxygen we need in this reaction. Okay, that's the end of the first section, and we're going to pause this video right now, or we're going to stop it, and we will continue on with the next section in the next video.